Center with those universities, and you should all visit that website. And we just have a formal methods in the field grant and the ARO grant that has supported a lot of the work. And just to keep it interactive, I think I kind of prefer questions as they're going on rather than at the end. Okay, so the genesis of this talk. A couple of years back, while I was doing some of the adversarial ML stuff, mostly with Nicholas and Patrick McDaniel, I was invited to speak at a place which was mostly control theorist, CAD, and some autonomous driving type guys. And as you know, what is our first in intro? What do we say? Autonomous driving, drones, so all these adversarial examples are suddenly going to crash all of these guys, right? And that's kind of our intro line. And essentially, when I gave the talk, it was mostly a survey of adversarial ML. It was a beat down. That's how I looked. And essentially on the plane ride back, it was basically an existential crisis moment. Essentially, we are solving the right problem? So I'm going to try to make it very provocative and see if you agree with me that are we solving actually the right problem as a community? Okay, I'm not going to, that audience I had to convince that how great ML is, not with this audience. ML is great, ML is used a lot, ML is beating doctors at prediction. Insert other platitudes about ML here. And as we know, if you look at the ML pipeline, every stage can be attacked. And as we attack different stages, you have, so for example, if you attack how the training data is collected, training set poisoning attacks. If you attack and you use the query interface to steal the model, that's a model theft attack. And I think Kamalika is going to speak about it tomorrow a little bit at her talk. And there are some attacks that you cannot, I don't know what they're called, I would call them fake news attacks, where you have generative models saying weird things like Obama saying he's a Muslim, right? So I don't know where that fits in. Okay, but what we are going to be talking about is in this space, which is adversarial examples, right? And since this is an AML talk, and if you don't show, so the definition which we're going to revisit was from a Goodfellow paper that I saw, which says adversarial examples are inputs to machine learning models that an attacker has intentionally designed to cause the model to make a mistake. Towards the end of the talk, I hope I can prove to you that this is not the definition we should be looking at. Okay, I need to be careful here. Okay, so if I can do that, the talk was successful. And at every AML talk, you should be shot if you don't show this slide, right? A panda becoming a gibbon, so here it is, don't shoot me. And same thing here, school bus becoming an ostrich. And my favorite one, cat becoming guacamole from, by the way, I really should, even though it's not my paper, I should plug it. I really like that paper. It's basically just using black box queries. And it is probably one of the most clever, I used to read about this in grad school, gradient-free optimization that Nesterov used to do. It's a very nice application of that. So it's not my work, but I still like that paper. And it has been extended beyond deep learning to various other kind of classifiers and also beyond computer vision. Okay, and as you can see, there's a deluge of work on attacks, defenses, applying to other domain verification algorithms. I think Martha is going to talk about that. And I cannot keep up, so if I don't mention your paper, don't be mad at me. Okay, so here is the definition that we flashed before. Adversarial examples are inputs that basically cause the model to make a mistake. I would like to say that what we should be working towards is this. Adversarial examples are inputs to machine learning models that an attacker has intentionally designed to cause the entire system which uses the machine learning model to make a mistake. And you'll see there's a difference here. For example, in an autonomous driving setting, I mean, I really don't care if a cat becomes guacamole. Like if I'm driving a car, I know there won't be a guacamole on the road, right? So what essentially these guys pointed out was there is a glaring omission from AML of the system that is using the machine learning algorithm. So for example, if I'm using ML for some smart drones, I need to be analyzing adversarial examples in the context of the control loop that the drone is using, and not just the ML algorithm that it is using. Okay? And if you want, this case is not new. This has been made, by the way, Dorsa is now a faculty at Stanford. It's a nice position paper which kind of makes that mistake, that point. So what I'm going to use is this as kind of my motivating example. It's a control loop for an automatic emergency braking system. And imagine that it uses ML algorithm mostly for perception. So for example, saying, hey, there is an object, there is a car in front of you at 10 meters and so on, feeds it to a controller which controls your car, and that interacts with the environment. So this is the closed loop system that I'm going to be using as a mock example throughout my talk. Okay, good. So yes?
I have a quick question. So I agree with your premise wholeheartedly.
Okay, then you don't need to listen to the talk. I convinced you already.
Well, my question is, do you have advice for those of us who our experience is getting a hold of real systems is impossible?
Yes, so let me, I will talk about that. So this is, I gave this talk at Berkeley, and David Wagner basically was saying exactly the same thing, that, you know, if you are a student, you get hold of MNIST, CFAR, you're off and running, right? And here, I agree with you that the benchmarks are not there, but I mean, I'm working on this mostly with people who are in this space, like Sanjit and so on. But I agree with you that lack of benchmarks is a big problem in this space. I completely agree. Okay, so enough of adding perturbations. You know, I'm sick of it. And what these guys care about is they want a richer set of transformations that you can apply to images to get adversarial examples. So essentially what these guys want is a DSL, a domain-specific language, in which you say, here are my transformations. I want to move a car to the other lane. I want to move the car closer to the car in front of me, and so on. And, you know, translation to make the, maybe make the background more cloudy. And what they want to do is, rather than your set of transformations is adding perturbations, I want to say, is there a sequence of operations in this transformation that I can like, which can actually disable the example? This is what these guys want. Anybody see a problem with this or not see a problem with this? So N of L infinity, LP, these guys don't care. Adding a small noise. So what is the problem? If you want to use these kind of transformations rather than just adding a delta for perturbation, what is the issue? Exactly. So you will have to now, what you have to do is, once I give you a DSL for these transformations, you will have to either make them some differential approximation of it or do something, okay? And that has not been explored, although somebody told, that paper is from Alex Mauthry's group, and it basically shows that a very simple rotation and translation suffices to fool some of the CNNs for adversarial examples. But they want much richer set of transformations. Rotation and translation is just one of them. So this is something that I think would be a very interesting project to go deeper into, is that if I have a simple DSL to kind of write these transformations down and then use that to actually generate adversarial examples. By the way, this is going to be the theme. I have more problems here than actually solutions. Go ahead.
Isn't the premise that you can capture this in the DSL already flawed?
So they do have DSLs for these. So yes, can you write all possible transformations that they can think about? No. But I can tell you, even having a smaller subset would be much bigger. They do not care about adding a small delta. That's not something that is meaningful to them. Okay? That is just not, I mean, literally they said this is irrelevant to them. So at least I agree that having a complete set of transformations is not easy, but even having something that is reasonable is much better than just using L delta with a small favorite norm. There's another question somewhere. Yes?
There's an ICR solution called benchmarking neural network with robustness to common interruptions. And so they do brightness changes, they do weather corrections, they do compression artifacts, they have like 15 different.
Yeah, so what these, so I haven't, by the way, I mean, this is a fast-moving field, so I'm getting all these papers in my mind and writing it down. But what they want is there's some sort of a DSL that these guys already use in things like some of the design tools that they sort of already use. So they don't want hard-coded sort of these transformations. They want a DSL that is differentiable, where you, because then I can run my favorite optimization engine to start generating out adversarial examples.
Like random corruptions work fine. You don't need to adversarially find them. Just evaluate non-IUD, like test error goes down or goes up a lot.
Yeah, let's take that. That's a longer answer to that. Yeah.
Well, actually, this rotation translation paper is a good example of this, where they show it's a small enough space that you can enumerate everything that worst case perturbations are much worse than average case ones. And it seems like that's maybe the problem, is once you start considering more and more perturbations.
You think there will be too many of those?
You just can't do exhaustive search anymore, which for rotation and translation.
Yeah, and they're fine with. I mean, the thing is, remember, these things are sitting in a loop where they're kind of debugging these scenarios. They're not interested in, maybe sort of full completeness or something like that. Okay. So essentially, this kind of semantic modification, which actually Sanjit's postdoc did it by hand, and essentially sort of moving the car over on the other side. Okay, so Florian and et al. Have a very nice paper which says which analyzes a space of adversarial examples and shows that the subspace of those adversarial examples has pretty high dimensionality. Was it in this NIPS or in?
We never actually published it anywhere.
Okay, so it is in the greatest venue of all, World Archive. So it's on that. It's published in Archive last year, I think. My hunch is, and I have some experiments that prove it, that if you define adversarial examples as that which suppose that actually screws up that control loop, the space of those adversarial examples is quite small. It lies in a much smaller subspace than sort of these vanilla adversarial examples. Okay? I will show you some anecdotal evidence. This is just conjecture. So in some sense, what I want to do is I want to design and generate adversarial examples that actually lead to system level failures. So actually will lead my car to brake violently or sort of faster than it should. And then obviously we all know this, we can use some of these adversarial examples for adversarial training. I'll say more about this later. So for example, again, a lot of the adversarial examples that we generated, again, this was done by hand because we don't have the DSL. We found that it actually fooled the object detector. So both those images actually fooled the object detector that was being used, which says that there wasn't a car. Okay? But only one of them actually caused the crash. The other was adversarial, but actually not a system level adversarial. And this is because, in a control loop, there are multiple sensors. There's the logic for detecting is much more complicated. And frankly, I think I don't know the entire control loop, so I won't tell you, but I think there's a lot more sensors there than just the camera. And the logic for detecting these is much more complicated. But we have plenty of examples like this that adversarial at the interface of machine learning of a module doesn't mean adversarial at the system level. Okay? And then you can obviously, once you have these counterexamples, you can do the normal thing of retraining your machine learning model. And what we find is that if you retrain on the actual examples that cause system level failure, your system does better, rather than training on odd adversarial examples. Good.
A quick question.
Yes.
Can you go back?
This
Just to
one?
understand these pictures, the red boxes where the system detected a car.
Yes.
Okay.
So it sort of screws up the bounding box
Yeah, yeah,
algorithm that they use. Yeah. Good. And I'm not going to go into the too much into the sort of the results. Okay. So the other thing that was pointed to me is that they use a lot of these people who design these control algorithms used a lot of techniques from designing robust controllers, and they don't like the fact that they cannot look inside. Even if you give them sort of cut at the softmax layer, even if you give them confidence values, they can do much more than just saying, hey, there is a car here, there's a cat here, there's a guacamole here, there's an ostrich here, right? So I think one thing will be is to sort of opening the box up a little bit more where, for example, very simple thing, right? I think we had an ICML paper 2018, which says that just by using model confidence, it can help some of the adversarial examples. And maybe going back to the two talks before, perhaps attribution can help, right? I mean, so for example, if I see some weird attribution, I can say, okay, I don't believe it. I'll rely on the other sensor. Just a shameless plug. A talk won't be complete without it. We have a paper that we'll submit to a conference coming soon, which basically shows that attribution gets better with adversarial training. Yes.
Does it pass sanity check?
Sanity check.
Yeah, the randomization test.
Okay, don't review our paper. Just kidding. No, I think that was a good. I think we didn't do that sanity check. Okay, we used the IG method, but that's a good point. It was big enough work because it was actually done in a company where they had to, it was a lot of work just to get the data set up. But so maybe what it is that if you don't use these ML models, which are being right now used as black boxes, but sort of open them up a bit, provide confidence values, or maybe attributions along with your prediction, maybe the people who are designing robust controllers on top can do better. Again, as I said, this is extremely just ideas. We have not been actually working on a lot of these. The last thing is what we have been working on. So for example, simple thing is, if there's a threshold, if the threshold is above a certain value for your confidence, you do break the car, otherwise you rely on a different sensor. Okay, now the last theme, this is where we have been spending a lot of cycles, is can we generate adversarial examples that matter, which essentially means adversarial examples that actually cause your control loop to do bad things, like break the car, okay? And this is now going into a little bit sort of formula method stuff, so people who are from the FM community might be a little bit happier, but I will have to introduce this before I actually talk about what we're talking about. So generally what we work in FM is what we call compositional falsification. So what you're given a formal specification of what you want, and I'll give you an example, and a model of your system, with like a control loop, plus the ML model, and you want to find inputs where M does not satisfy phi. Okay, so that's why it's called compositional falsification. And it's called compositional because you don't want to compose all these models together. You want to do compositionally in treating the models separately, otherwise it will blow up. Okay. Now the big thing here is, how do we handle the ML component? So I pull Inception or the latest version, use it. What does it mean to verify it in this context? Let's do a study here. As we know, once you train the neural network, it's a program, right? A mean, I don't care how you train it. Once you post-train, it's a program. We have been doing with formal verification of programs for decades now. I will just treat it as a program. And it is even easier, right? It's a loop-free program. There's no, generally, most of the ML programs don't have loops. This will not work just because the size is getting too large. Okay, if I just don't do anything special there, so the idea is that you just put your machine learning model and let my program verification sort of thing handle it and how it happens. Okay? The problem is it's getting too big, and it just sort of, at least most of the verifiers will just die. The other thing is I use adversarial examples like PGD or Carlini-Wagner or whatever as a black box, keep throwing adversarial examples, and then use my loop to check whether it's an system-level adversarial example. Now the problem is this is what is the conjecture I told you, that I think the subspace of adversarial examples that actually cause the system to fail versus the whole space of adversarial examples, I think there is a big discrepancy there. So this you will be sort of using a lot of resources on just false alarm, so to speak. Okay. So in some sense, we want to have a compositional verification framework where we actually don't model the machine learning component. Any ideas? So we want to verify we don't want to verify the object detector that is being used in my loop, but I want to verify the entire system that contains it. So any sort of first level thoughts? Yes?
People have demonstrated system level adversarial examples with iPhone. You can construct a 3D model of the iPhone under space and it will unlock the phone. Also, iPhones like confuse
Yeah, but remember here I'm given a special, I'm giving a specific control loop where this is some object detector, think YOLO or something like that. So it's not just detecting on, here the specification of the control loop is given by the car manufacturer or whoever is doing that.
You want the car not to fail in any setting.
No, I want that's a much harder problem. Compositional falsification only says I want a trace in which the car actually fails. I want a counterexample to fail. So let me write that down. So here is this is the temporal logic that says the distance between the vehicle and the object is always above a certain threshold. I want you to show a scenario, which is like a sort of a scene, the velocity of the vehicle, so that this entire control loop falsifies that statement.
But where is like breaking the system sensors?
That's in the control. I didn't do the whole control logic.
Wait, how are you going to guarantee that no one like breaks the sensors on the car?
Yeah. Okay. Again, let's pick our battles here. If you get into the car and you sort of really mess with all the sensors, sort of fine. So what I am interested in is imagining think about this way, our TCB is actually here. You could change this, that's what adversarial examples kind of do, but then what I want to do is somehow make sure that it screws up the whole logic. Again, you seem confused. Okay, go ahead.
I mean, it's fairly naive, I guess, but I work my way backward until I can find an input to the controller that's a realistic output of the network, and then I would construct my adversarial search to look for that output.
Yeah, not bad. I mean, 50% there. Yes. So in some sense, you want to kind of sort of narrow down the search that you give here for the adversarial example.
Yeah, it's something that's
Yeah.
a trace through the rest of it.
Exactly. So this is what we sort of let us do a thought experiment that will be much clearer. If this classifies an object correctly and the system fails, well, then it is not the machine learning guy's problem, it's a problem with the controller. That we know how to handle, or we meaning some control engineer. If this guy misclassifies and it actually doesn't cause the loop to actually do anything bad, well, we don't care about that misclassification, correct? If this misclassifies and that's what gets the controller to misbehave, that's the misclassification we want, right? So there are these three things, and that's the space that we want to somehow get hold of, the third space, right? And this is what we do. I'm not going to that is the system level component of what's called breach, the system that actually verifies the control loop. I'm not going to get into that. What we basically do is we do a pessimistic analysis, which basically says the machine learning algorithm is always wrong. Okay? Then we do an optimistic analysis using some abstraction, which basically says the machine learning system is always right. Okay? Now let me show you what happens. This is the ML system always correct, and red is the system fails. Those are the trajectories that fail. Those are where the ML system is always wrong. That yellow is basically what we really want. That's a subspace that we want. And the analysis that we do actually gives you, now again, it's an over approximation of that, gives you that yellow space, which is exactly what you were talking about, right? Because the idea is that if the ML system is always wrong and you were still in that green good zone, well, that I don't care about. So I basically want to care about things where when the ML was, the algorithm was always right, I was in the green space, but then when it was misclassified, I went into the right space. And then essentially what you do is you search only in that subspace, which hopefully is much smaller than what you have. 4 minutes. Okay. Now, using this sort of technology, we were able to generate some weird images that, at least for the model of the control loop, was able to actually cause some damage. The car, really sort of, the braking system activated and so on. But we were able to generate a lot of misclassification that actually did not cause the whole system to fail. There were lots of them. So that again comes back to the same conjecture that I had before. Now, this kind of thing led me to believe this is probably the most kind of out there slide, is that most of, even now the car detectors just use ML model out of the box. They will use some object detector like YOLO, SqueezeDat, or something like that. And then they still use the pre-trained model. That might be too hard a problem. Can we somehow modify the loss function or something where we basically are able to give our machine learning model some guidance saying, hey, those other misclassifications I really don't care about. But in that subspace, the cost of misclassification is really high. Don't do it. And I don't know, first of all, I don't know how to give a differentiable handle to that space. So this is something that is very, very interesting to me. And if you have ideas, let me know. I just have no idea how to do that. How to sort of modify the loss function of the model so that you're basically steering it towards misclassifications that matter, and you tell them that, these other misclassifications, I really don't give a damn. You can misclassify that as much as you want. Some question, yeah.
Isn't this concept independent of adversarial ML?
It is. Yeah, but I'm hoping that this will at least make them robust to system-level adversarial failures. And actually, we tried some very simple things, some version of hinge loss, which did actually reduce the impact of the collisions and so on. But this is something I think will be very interesting if you can actually do it end-to-end. Okay? Now, there is some work going on, and maybe this is something where people are trying to, so for example, train neural networks which gives very succinct explanations. And I think this is this here. I hope I didn't get the. And it is in the same vein where what you're basically saying is, the logic for things, what matters, can I pass it as during training to the machine learning algorithm, such that it sort of, misclassifies it only in the space that doesn't matter. So I think it is. I haven't this is something that just some people told me that this work might be sort of related to my last theme. And that's it. So I mean, are we solving the right problem? Just small unlocking of iPhones, these things. To me, this is not sort of the right granularity. What is right is you should be working with control theorists who do these full control loop verification and sort of trying to plug your sort of technology there. I think that's where we are going to have real promise. But again, this is messy, right? This is not about just downloading the next data set and you get a pre-trained model and you do some work and you have a NIPS paper. I mean, even to get these simulators working, it takes months, and to understand what they're talking about takes months. So just to get a student working on this is probably 9 months to 12 months before they even get to the ML problem. Yes?
So you're talking about how to get the information about where the important failures lie
Yes.
back into the neural network to inform its loss.
Mm.
So I don't actually think this is a good idea, but I want to hear why it's not a good idea just to use reinforcement learning and have some reward function about,
Yeah, but then reward function has to be sort of, informed by saying that, hey, that's the region, don't get into that. Is that what you?
I don't think it does need to be informed by that. It just needs to say how bad the different.
So
crash
at least, and I'll tell you what I got from that crowd that I presented to.
Yeah.
Some of the RL loops are too slow for them. They do use some version of reinforcement learning, but somehow there was this. I want to say that anti-RL sentiment, which I didn't understand.
The learning happens too slowly, or not sure.
I'm not sure. I'll have to probably. I can ask some of those guys. By the way, there are conferences in this stuff like smart cars and smart innovation and so on. And we should be presenting there. So my feeling is if we don't solve this, I really do think that we are not really solving the right problem. There is a difference between writing papers and solving problems, right? So this is what I sort of wanted you to take over. And hopefully you're as puzzled as me that am I working on the right things? These guys convinced me that I was not. Again, I also want to say that, based on this question, these little sort of toy things like unlocking iPhones and all that, it's much easier than some of these control loops that I just saw. Okay, because there you really need to understand some of these sort of robust control stuff that they were using there. And there you have to take these specs and sort of try to, analyze them.